I welcome all the students to Pune College of Arts, Science and Commerce, Camp Pune 1. I teach SYBA, Subject Statistics General, Sampling. Myself, Dr. M.B. Pathan. In last lecture, we have discussed about unbiased estimator of population mean and its variance under the sampling method known as simple random sampling with replacement and simple random sampling without replacement. We also took a simple example to illustrate these both topics. Today, we'll try to see the unbiased estimate of population mean sum of square under simple random sampling without replacement. The question may be asked on the topic as show that sample mean sum of square is unbiased estimator of population mean sum of square. That means expected value of small s square equal to capital S square. The heading of the topic is unbiased estimate of population mean sum of square S square. When I say estimate, it is a particular value, and if I say estimator, it is the functional form of that estimate. So expected value of small s square, this is a sample quantity. Its expectation is exactly equal to population mean sum of square. When expectation of sample quantity is equal to population quantity, that is called as unbiased. If this is not equal, something is extra plus minus, then this is labeled as bias estimator. We can see the proof under without replacement. Consider y1, y2, yn be a random sample of size n drawn by simple random sampling without replacement. So we have sample mean sum of square formula as small s square 1 upon small n minus 1 summation I1 to small n bracket yi minus y bar square. We have seen this formula before also under the notations. Now, from your first year knowledge, we know that this quantity can be simplified. This entire quantity can be simplified as summation yi square minus n times y bar square. This will be simplified further like this. We know that sample mean is summation yi upon n, here square, so continue as a square. Now this n square will be taken out with cancel with small n, remaining is 1 upon n, sum of yi squared. I told in the last topic, sum of variable with square can be written as addition of two separate quantity. So this is equivalent to this curly bracket. This we have seen in the last derivation. Therefore, we get a simplified term of s square. That means from this formula till here, we have not made any changes. It is only simplification of original formula. So we get small s square 1 upon n minus 1. Here sum of y square, here sum of y square. If I take a common from this quantity, you get 1, and this is multiplied by minus 1 by n, so we write like this. Minus 1 by n multiplied for the second term. Now this bracket can be simplified as n minus 1 upon n. After this, we go next step as 1 upon n minus 1, n minus 1 upon n, summation yi square minus 1 upon n, summation yj, I not equal to j. If I multiply this outside factor inside, this n minus 1 get cancelled with this n minus 1. So we get a simplified expression for sample mean sum of square. This is your sample mean sum of square. 1 by n sum of y square minus 1 divided by n multiply n minus 1 summation yj I not equal to j. Now from this step onward, we try to decide what is the expectation of this quantity. So expected value of left side is equal to 1 by n. Expected value of sum of y square minus 1 upon n into n minus 1. Expected value of sum of yij. I call this expression as A, circled A. Now I try to develop this expectation separately and this expectation separately. Expected value of sum of yi square equal to summation I1 to capital N, expected value of AI, yi square. Now you can see the comparative left and right. Left hand, it is the expectation of sample quantity which is transferred as a population quantity with the variable AI as an indicator variable. AI takes two values. One, if population include in the sample, it is 0 if sample unit not included in the sample. So both are equivalent terms. We proved in the previous topics expected value of this variable is n upon n, which is a constant taken out. So you got the answer for expected value of summation yi square is small n divided by capital N, summation yi square I from 1 to capital N. Similarly, expected value of summation yij I not equal to j. Expectation goes inside by your first year knowledge. Expectation of sum is sum of expectation. So I took expectation inside summation. Similarly, as previous step, I took help of two indicator variables, ith unit included in the sample, zth unit of population included in the sample. If they are included, this product will be 1. If any one of them is not included, product will be 0, because this both variable takes either value 1 or 0. Again, we proved in previous topics, expected value of AIAJ is n into n minus 1 divided by capital N into n minus 1. It is true under simple random sampling without replacement, because at ith first selection there are n sample unit to be selected from capital N. Under without replacement, for next draw, sample unit to be selected n minus 1 and available units are capital N minus 1. That's why expected value of AIAJ is coming this much. Summation capital YI capital YZ. Now I replace these both expressions in equation A to get a simplified term. Therefore, expected value of S square 1 upon n multiply n by capital N summation yi square. This is from where? This is written from this step. 1 upon n outside and expectation yi square, we got this much. So we put it in proper place and we simplify further. This small n get cancelled. 1 upon capital N summation yi square minus this small n minus 1 get cancelled with outside. Capital N upon multiply n minus 1 remain as it is. Sum of product, we have seen previous topic, can be written by subtraction of two quantity like this, because sum of yi square equal this plus this. That's why you can interchange side, you get this much. 1 upon n summation yi square, this minus and this minus become plus, so I write here plus quantity, minus 1 upon n into n minus 1, sum of yi is nothing but n time y bar, because y bar is summation yi upon n. So you can write y bar multiply n as total of yi's. So this is written in this way. Further now, sum of yi square is a common term. We take out, so inside bracket 1 by n plus 1 upon n into n minus 1. This is simplified. If I take a square inside, it becomes n square. Power cancel with denominator n. So you get n time yi square, y bar square upon n minus 1. Now this will be simplified by taking LCM n into n minus 1. N minus 1 comes here, plus 1. Minus 1 plus 1 get cancelled. N get cancelled with this n. So balance term is 1 upon n minus 1. sum of yi square minus ny bar square, denominator is n minus 1. So finally you get 1 upon n minus 1 bracket sum of yi square minus n time y bar square. And this entire term, if you recall your notations given by me, this represent population mean sum of square. Hence we proved expected value of sample mean sum of square is coming to be population mean sum of square. We can write this statement in this way. This is nothing but another way of writing the same statement. If I drop this capital E as an expectation from left, it goes as a cap on the right hand side. So how to read? Estimate of s square equals small s square. That is the way of reading this notation. Therefore, conclusion of the topic is sample mean sum of square is unbiased estimate of the population mean sum of square. You can say same thing again. Sample mean sum of square is unbiased estimator of population mean sum of square. If I say estimate, it is the particular value of estimator. Remark, with the help of this proof, we can prove another topics also. That is under remark. The estimator of variance of sample mean is variance of y bar under without replacement equal to n minus n divided by n into n s square. If you drop this cap, this we have proved in previous topic. Variance of y bar is this much. I want estimate of variance. That means population size, sample size are fixed. Estimate of variance is nothing but estimate of s square. And we proved estimate of s square is small s square. So in exam, if they ask, obtain the estimator of variance of sample mean under without replacement, then you have to make all these derivation, and at the last you just claim these two lines. That will be the answer of this question. Sometime to confuse the student, they use standard error word instead of variance. So estimator of standard error, after proving this much, take the root, and root of this quantity s square root will be small s. This will be answer for standard error. So with the help of this proof, you can give another answers which can be called as a corollaries coming from the main proof. Now we proceed ahead. Take a simple example to understand what I did for proving unbiased estimate of population mean sum of square. A consignment of 5,000 items. A random sample of 10 items selected by without replacement. The corresponding values of the items are given to you. The question says we have a population with 5,000 items. Capital N is 5,000. From this consignment, we draw a sample of size 10. The method is given to be without replacement. Question: compute average weight of the consignment. Also estimate total weight of consignment. This question is not related with this topic. It is previously what we proved. Sample mean is unbiased estimator of population mean, and we can find estimate of population total with the help of sample mean. So this is the repetition of that topic. We have n equal to 5,000. Sample is of 10 items. Get a sample mean, that is 24.2. Population mean estimate is the sample mean we proved before. So this is the average weight of consignment in a particular consignment. If I want to decide the total weight of the consignment, y cap is n times sample mean. N is 5,000, sample mean is 24.2, answer is this much. You can put the weight units. If it is grams, write grams. If it is kg, write kg. Units should be assigned. Now we have next question, a population of 5 units. Assume the values 3, 7, 10, 8 and 5. Draw all possible sample of size 3 by without replacement. Verify. Bit number A, sample mean is unbiased estimator of population mean, which is a repetition of previous example. Bit number B, variance of sample mean under with replacement is greater than variance of sample mean without replacement. And you have bit number C, find the variance of sample minimum square. We'll try to see this A, B, C, how to solve. It is given that population of 5 units, it is only for illustration. Otherwise, in actual practice, population is very large. And that is why we take a help of sampling. From this, we take a sample of 3 units and value of units are given to you. We have mean of the entire population, addition of all 5 values divided by 5, that is 6.6. We can calculate population variance directly denoted by sigma square. Population variance always denoted by sigma square. Summation I1 to n yi square upon capital N minus y bar square. It is a simplified formula of variance, what you studied from your first year knowledge. Yi square, this is the first element of the population, square it, plus second unit of population, square that. Do like this for every population unit. Minus population mean is 6.6, make a square. After simplification, 5.84. This represent value of population variance sigma square. Now you can get population mean sum of square. Notation is capital S square. There is a small change little bit in the formula. Instead of capital N, we write n minus 1. And here it will be minus n time y bar square. You can see the notation. Here you have to see the perfect formula which is not coming nicely in the scan copy. This is 247 sum of yi square minus n time y bar square. Total divided by n minus 1. Answer is 7.3. So I calculate population mean sum of square. I calculate population variance. I calculate population mean. So this is the calculations related with population quantities. Variance of y bar under with replacement we proved before sigma square by n. N is the sample size 3. This we calculate before. So answer of variance of y bar under with replacement 1.94 and variance of y bar without replacement 5.84. Easily you can see with replacement has smaller variance as compared to without replacement. Under without replacement, variance of sample mean is n minus n upon n into n s square. This all formulae we derived before. You can see my videos which is uploaded on YouTube, and if you have doubt you can discuss. Put the proper values and get simplification. So you get 0.9733. This says that variance of sample mean under with replacement is bigger than variance of sample mean under without replacement. Next, total samples by without replacement n choose n equal 5 choose 3. If you simplify the formula by combination, the simplification comes 10. So what this number says? It says that you can study population of size 5 by picking 3 elements with totally 10 different weights. Let us see what are the 10 different weights. Serial number 1 to 10. These are the samples selected. 3, 7, 10. These are the curly bracket notations. 3, 7, 8 and so on. Sample mean. Then for every quantity yi minus y bar square, that means this is a calculation yi bar 6.667 minus y bar is a population mean and get the quantities. Sum of this column is 9.7334. Sum of this column is summation yi bar because this each of them represent sample mean. Now expected value of y bar, that is a sample mean, is summation I1 to 10 because 10 samples are there. Y bar I divided by 10. This is the total of numerator divided by 10. It comes 6.59, that is 6.6, and this we have done at the beginning. Population mean is 6.6. So this numerical example illustrates expected value of sample mean is coming a population mean. We can write by the notation y bar cap equal to small y bar. Small letter for sample quantity, capital letter for population quantity. Variance of y bar under without replacement we got before 0.9733. And variance of y bar, you can use this as your total of numerator divided by 10, that is also 0.9733. So both quantities are similar. So you can say small s square is unbiased estimator of population s square. You have similar questions, you can go through it. If you have any type of doubt, you can discuss with me. These are all calculations which is similar to previous examples. That is the end of sampling with variable characteristics. That means when you study a variable which is a measurable, length of the rod, different examples, life of some equipments, these are the measurable characteristics. Then you can use sampling with variable characteristics. But many times in the real life, we are not interested in the measurement, we are interested in the quality of the product. So quality of the product will be classified as good quality or bad quality. If product satisfy the customer specification, that product is good for customer. If product does not satisfy customer specifications, then we treat that product as a bad quality. So if you classify entire production in two categories, favorable and non-favorable, so that sampling will be treated as sampling for attributes, or you can call sampling for proportions and percentages. This is a new topic. We'll try to discuss this new topic in next lecture.